requirements. Think about how to start forming it into code and algorithms and stuff. So started with conceptual design, and then we so that includes like the relational model, ER model, and everything. And then we kind of just skipped over this schema refinement part. And we've talked about physical design, indexes and disk layout and stuff like that. We didn't actually skip number 3. We've been talking about it the whole time, but never really in a formal way. So you'll see what I mean by that. But it comes down to like more guarantees about consistency and something called normalization. So remember from way back in the beginning, one of the things we were trying to avoid in schema design is redundancy. So I asked the question, like, if we were trying to build a library, how do we represent a person checking out more than one book? And one of the options is maybe just, if they're all in one big table like this, you'd have to just put in multiple rows, including 3 copies of Malfoy and his phone number and his card number and everything. Kind of another way to phrase this issue is, what if the same book is checked out by multiple people, or if you have multiple copies of the book? And obviously this is not what we do. This redundancy is bad for the obvious reason, which is storage, but very bad in even more important ways, which is, now I have all this duplicated data. What if I change Malfoy's name? I have to go and find everywhere where that exists and change it in a lot of places. But let's look at maybe a different approach. So this is back to an LMS instead of a library. This is a modified version of what I've been showing, and this is not, hopefully not, the way you've designed your tables. So I have students and enrolled, but I've added name. I've copied name into enrolled. The reason you might want to do that is, now if you had a common query, if one of your common queries was give me the names of all people in a certain class, now you can do that without a join, right? So if enrolled did not have this name column, I could still do it, but I'd have to join on UID, join these 2 tables on UID. So maybe that does speed it up, but actually not really. If you have proper index on these tables, then the join is basically free. It's not actually turning into like an n² multiply here. And we've seen that. We've been looking at joins and indexes and the plan generator a lot lately. So no, definitely don't add a name column to the enrolled table just because you want to speed up one particular query. So why not? The basic problem, which I already mentioned, is duplicate storage. You don't want to have a whole bunch of the same name everywhere. The bigger problem is more of a design problem, because it introduces what are called update, insert, or deletion anomalies. So anytime I do an update or an insert or a deletion, those are now non-trivial. Okay, so let's say Harry decides to change his name to H-Dog. Having never read the books, that's his character in my mind for some reason. Now I have to go find every class he's enrolled in, and I have to go and update his name there. What if I also did this in some other table? What if I did this in like the assignment submissions table? What if I copied name into there to speed up some query? I'd have to go and find that table and update his name everywhere. Okay, fine. Maybe go and update all those names. But Now a simple update won't do it. A simple loop that says go find the other tables and update everything, that's not going to work, because what if the power goes out during the middle of that? So not only would you have to update everything, you would have to do that inside of a gigantic transaction involving every table where this duplicate name is used. And this just makes it harder to even remember what you have to do. The programmer or the DBA has to know, okay, let's see, what other tables did I copy this column into? Where do I have to go and update everything now? So it just makes the design a nightmare. This is a much bigger problem than the duplicate storage problem. The storage is fairly cheap. Okay. So, the main way of fixing this kind of problem, of refining tables that have this kind of problem, is called decomposition. And we've seen this before. I just never really gave it this name. But basically, you take one table that has a bunch of columns, and you split it into two with some way of getting in between them, some kind of foreign key. So if I had A, B, C, D, I could decompose that into A, B, and B, C, D, or lots of other various potential combinations. That's the basic idea. And you're familiar with this. We've done this, just not formally with this name. So you could go the extreme and just say decompose everything. Make a whole bunch of like 1 or 2 column tables. I could take students and decompose it into just UIDs, and then UID combined with name, and then UID combined with date of birth. But there is absolutely no reason to do that, because all of these things are directly related. Put them all in one table. So, don't decompose if there's no reason to. Do decompose if there is a reason to. So how do we know if there is a reason to or not? You all have probably, hopefully, a pretty good idea of should you decompose a table or not. But today we're going to talk about the formal language and formal way of thinking about this, basically rules. Should you decompose this table or not? So you all have probably come up with good designs for your tables, but let's say you inherited somebody else's design and you want to verify that you don't need to do any decomposition or refinement of those tables. Okay, so how do we know? The basic tool for asking and answering this question is called a functional dependency. So if we can identify functional dependencies and reason about, like, does this functional dependency matter or not, then we can just say, if yes, then we can decompose the table and eliminate these anomalies, where if I change somebody's name, like an update anomaly or an insert anomaly. Okay, so what is a functional dependency? We kind of notate them X arrow Y. Basically what this means is that X determines Y. So X and Y are subsets of attributes. So, a single column, a set of columns, some subset of columns on a relation, the same relation. So maybe as an example, X is UID and Y is name from the student's relation. Or X is UID and Y is the combination of name and date of birth. So these are just subsets of fields of columns from some table. Okay, so this is not the full definition. So what is a functional dependency? What this means is if I have a functional dependency from X to Y, remember X and Y are columns. If I take any 2 tuples out of the table and project out X from T1 and project out X from T2, if those are equal, then that means that their y values are also equal. So if I project out the x's and they're equal, then if I project out the y's, they have to be equal, if the functional dependency is true. Okay, so this is for all possible instances of some schema. So whether you have 5 students in the table or 100,000 students in the table, pick any 2 tuples. This has to hold. Okay, so it's kind of, let's put it in kind of more English terms. A functional dependence xy means basically that x determines y. So take 2 tuples. If their x values are the same, then their y values have to be the same. So simple example of this. These 2 tuples can be the same, by the way. They can be, T1 can be equal to T2. So if the UID is the same, then the name has to be the same, right? Somebody with a UID of 1, there's only one person with a UID of 1, which means that is the one person with whatever name they have, Hermione. Okay, but this does not go the other way around. So functional dependency x to y does not imply functional dependency y to x. We'll see, you might be kind of thinking, well, how is that possible? We will see an example of that. Okay, here's a student's table. What are the functional dependencies here? You know that UID is the primary key. So anyone, give me a functional dependency. Yep.
So it should be UID and name, right?
UID and name. Yep, there's one. Any others?
UID and date of birth?
UID and date of birth, yes.
Everything depends on UID?
UID to everything, yeah. So I'm abbreviating here now. U for UID, N for name, D for date of birth, G for GPA. So there's a functional dependency from UID to the full set N, D, and G, or any subset of that. So U to D, U to N and G, any combination of the other columns. Yes?
So the other subset can change, like GPA can change, is that what you're telling me?
So GPA can change, but what?
Sorry, so it doesn't matter if Y can change?
If Y can change,
Like the GPA can be higher or lower, depending on the year.
the GPA can be higher depending on the year of birth.
No, so if I get UID and GPA, then even if GPA can change.
Oh, I see, yes. Yes, so UID determines GPA. GPA does not determine UID. So yes, a person's GPA can change without their UID changing.
So in the functional dependency, your starting point is always going to be a primary key or unique key, and then it leads to just some subset that links.
Right, so for this particular functional dependency, this is heavily tied to the primary key. This is not really anything new. We know that a primary key uniquely identifies a row. Therefore, the primary key determines everything else in that row. So yes, the question was, do we kind of start with the primary key when looking at functional dependencies? Yeah, those are kind of the obvious ones. But there are, if that was all it was, then this wouldn't really be very interesting. We know all about keys and primary keys. But there are other functional dependencies that don't involve keys. For example, I've added a new column now. I've added a column called funds, like scholarship funds or something. So any other functional dependencies here? Well, you can't really answer that without me telling you what the rules are. We can look at this and see, okay, well, both of the people with a 3.9 have the same funds. The only person with a 4.0 has the same funds as that only person. But so what I'm what I'm not telling you is, yes, we want that to be a rule. We want for the amount of scholarship money somebody receives, we want that to be tied to their GPA. This is like, if that is the case, then we can prove no discrimination, basically. If scholarship funds is strictly related to GPA, then two people with GPA have to receive the same amount of funds. So if I specified that, I would say that there is a functional dependency from GPA to funds, or G to F. And the kind of English version of that is any two students with the same GPA that have the same funding. This is if I wanted to add that additional rule. So this is just a functional dependency that I have said, well, we should have this in our table. Okay. Now, what if I add another student here with these values? So GPA of 3.7, funds of 8K. Does this violate my functional dependency? I see some head shaking. Anyone want? Yes. Yeah, it does still hold. So do all, take any pair of people with the same GPA, do they have the same funds? Yes. So this is an example where G to F does not mean F to G. Or, X to Y does not mean Y to X. I can have different funding levels for different GPAs, but I cannot have the same GPAs get different funds. Okay. So let's look at this schema. And let's say I do want that restriction, that functional dependency. If this was my table, then this allows for those three anomalies I talked about. The table itself is not preventing me from just going in and changing someone's GPA without also changing their funding. Or it lets me, say I want to insert a new row. How do I know, say I know their GPA, how do I know how much money to give them? I would have to go and find another row with the same GPA in order to figure that out. So I'd have to do another select, be like, okay, we'll go find somebody else with that GPA and then tell me how many funds to give them. Another problem here is, say I delete every single student with a 4.0 for whatever reason, then we've kind of forgot how much money the 4.0 students should get. We've lost that mapping because it's not saved anywhere else. If the student gets deleted, if all such students get deleted, then the mapping is also deleted. Okay. So to fix this, we decompose the relation. We take the functional dependency, so it was GPA to F, GPA to funds. We make a new table that contains those two columns, and then we add a foreign key. We keep a foreign key in the original table that goes to G. Okay, so we have to still have GPA in students, but now we have this other table that maps the funding rates. It's not tied to any particular student. This is just and that's exactly the point, is that this is now non-discriminatory, like anyone with a whatever GPA gets whatever funds. Okay. And you make the thing on the left of the functional dependency, you make that the primary key in the new table. Okay, make sense? So this is kind of what I said, we've pretty much been doing this all along, we've just never formally described it.
So is functional dependency just sort of like a sort of theoretical schema thing, and then foreign keys are how you actually implement it?
Yeah, so functional dependency is more an abstract, high-level notion of what the data should mean, and then decomposing the actual tables and using foreign keys and primary keys is how you implement it. Yep.
So does that mean that every time you have functional dependency, it implies the application of the primary key?
So does that mean that every time you have a functional dependency, you should either decompose or the thing on the left of the functional dependency should be the primary key? Kind of. So that kind of depends on how strict you want to be. This is a valid table. So the question is, do I care about this functional dependency enough to do something about it? And there are various sets of rules you can follow. You can say, I want to pick they're called normal forms. You say, I want to follow the first normal form. And then you only follow a certain set of rules. There's second normal form, third normal form. We'll talk about those, and then basically you kind of just say, if you can prove your tables are in a certain normal form, then you can prove certain things about your entire database. Okay, so similar to keys, given a table, we cannot infer its functional dependencies. But given a table and a functional dependency, we can verify if that functional dependency holds. Okay, so given this table and a functional dependency, UID to date of birth, yes, we can prove that. Given this table and no functional dependencies, can we infer what the dependencies are? No. You might say, well, looking at just this information, I would say that there is a functional dependency between name and date of birth. Because everyone with a certain name has a certain date of birth. Because I don't actually have two people with the same name in here. That doesn't mean that it's impossible. So I can't infer that there is a functional dependency from name to date. But I could, if given that functional dependency, I could tell you whether this table violates it or not. Okay, so kind of back to like the whole design process. We kind of start with the basic idea, and then we go to an ER diagram. So this is if you are working through the design from start to finish, rather than if you've inherited a design. We'll get to kind of that. But so here's a simple ER diagram saying, there are professors and departments. A professor works in a department. So subject is the key of a department, like CS or ME or whatever. And then let's say I wanted to add a functional dependency that all professors in a certain department must work in the same building. Okay. So this is kind of, in other words, it's like subject determines building. So S arrow B. How do I fix this ER diagram? Like what I've said so far is the way that we fix these problems is by decomposition. Turns out to fix this functional dependency, or not to fix it, but to make these tables support it, all we do is move building from professors over to departments. Okay, so every single professor should not say what building they work in. Like every single CS professor would then have in their row in the database, they would have MEB. That's a lot of redundant information. And if you changed, if we suddenly got a new CS building, you'd have to go and change every record from MEB to whatever the new building is. If instead you put the building on the department, then there's one mapping, one record of that, and if you change buildings, you change it in one place, and then magically every professor has changed buildings. So you don't always use decomposition. I didn't have to make a new entity set. I just moved an attribute to another one. But Remember, these are not tables. This is an ER diagram, so decomposition doesn't really even apply. We're not dealing with tables, so we can't split a table. Okay? But just kind of a different way to think about it, whether you're dealing with ER or tables. Any questions? Yeah.
How possible is it to say if in the future you would come to this company that's built this whole database and they've been putting applications on it for years, so there's numerous applications looking to these tables specifically. Is it even possible to use decomposition at that point without having to go through and fix?
Yeah, so if you have some database with tons of momentum and tons of applications using it, the problem certainly gets harder. Like if you just decide you need to decompose a table, it might be actually no big deal, but depending on like foreign key constraints and everything, it might actually be almost impossible. So that's kind of why it's important to get the design right before you get too heavy into using it. Okay, so now don't start to get alarmed by notation and symbols. We'll kind of walk through all this. But so going back to, let's say you inherited somebody's design, and you want to be able to prove certain things about it and know whether you should refine it or not. So dealing with functional dependencies and proving things about them, we have these three things called Armstrong's axioms. So and X and Y are, again, like subsets of columns from some schema. So reflexivity means if X is a superset of Y, then there is a functional dependency from X to Y. And we'll go through an example of each of these. Augmentation. If there is a functional dependency X to Y, then I can pick some Z and augment both X and Y with that Z. And we get a new functional dependency, XZ to YZ. And transitivity means what it's always meant. If X determines Y and Y determines Z, then X determines Z. So examples. Reflexivity. If X is a superset of Y, then X determines Y. So let's look at an example. X is name and age. Y is name. If I have somebody's name and age, then I know their name. That's all that's saying. If I have somebody's name and age, then I know their age. Okay, so simpler than the notation makes it look. Augmentation. If I know somebody's UID and their name, so if I'm saying a UID determines a name, then I can also say UID combined with date of birth determines name combined with date of birth. Also kind of not that mind-blowing. But these are like kind of fundamental properties that we can use to reason about more complex and abstract dependencies. Kind of like the basic rules of algebra. Sometimes the rules are not that mind-blowing, but their applications are very useful. And then transitivity. The example we've actually seen of this was there was a functional dependency from GPA to funds, and there's a functional dependency from UID to everything, so UID to GPA. That means that a UID also determines somebody's funds. All right, so if I go back to this table, can a UID determine how much funds somebody is getting? Yes. Even after decomposing the tables like this. Since UID determines GPA and GPA determines funds, UID determines funds. Okay. Some additional properties that kind of come out of those axioms. if there's a functional dependency from x to the complex y and z, then that also implies that there's one from x to y alone and one from x to z alone, but not the other way around. So if there's a complex y-z determining x, then you can't say that y determines z, and you can't say that z determines. Sorry, you can't say that that is a typo. I should say you can't determine that y determines x or that z determines x. Okay. Kind of similarly, if x determines y and y determines z, then x determines the complex y and z. So we're not going to make you prove any of this stuff, really. Don't get too hung up on this. This stuff all makes basic sense. If you kind of have to go back and review and like write down a couple of examples, but it's pretty easy to kind of prove it to yourself. Okay, and then finally, there's something called a trivial functional dependency, which is, my colors are all messed up here. If x determines y and y is a subset of x, that's called a trivial functional dependency. So if I have name and GPA determining name, that's trivial. Anything, so x determining x is also trivial. Obviously, anything determines itself. Okay. And then there's this notion of closure. Okay, so if I have some known functional dependency or dependencies, f. So f is a set of known functional dependencies. Those are only the known ones. They're using those Armstrong's axioms. There are potentially a lot more functional dependencies that you can prove. And that's called the closure of f. So given f in the simple logical rules, this notation f plus, that's called the closure of f. That is all of the functional dependencies you can prove given some small set of known functional dependencies. So for example, if I know that UID determines everything and GPA determines funds, there are other functional dependencies I could make out of that. That's called the closure. Okay, so that's kind of the basic formal language. We will use that to discuss, like, how do we use this? What can we do about it? How should we refine our tables? So let's take our 5-minute break now. You pretty much already are following the right practices. And so today's lecture will actually be probably a little short, but we do have some more to get through here. So all of this stuff can be used to define what's called a normal form. A normal form is basically a set of rules, and there are multiple normal forms. So like first normal form, second normal form. These help you answer the question, should you decompose your tables or not? They also help you say, somebody says, yeah, my database is in first normal form. Then you can say, okay, I immediately know what that means. Certain rules hold for every relation in your database. And so we'll talk a little bit about first normal form and Boyce-Codd normal form. In between those are second normal form and third normal form. So here's first normal form, which was like the number one rule I gave you on day one, is that all attributes are atomic, meaning you can't have a list or an array or a set or anything like that in a field. That was one of the possible options for the question, what if somebody checks out multiple books? Well, maybe make it an array. Ron has an array of books that he's checked out. That would be violating the very first normal form. And that's all first normal form is. We solve that problem by decomposing tables. So there's second normal form, third normal form, which we won't really get into much because second normal form requires first normal form plus some additional rules. And then third normal form is second normal form plus some additional rules. We'll talk more about Boyce-Codd normal form, which could, in spirit, kind of be called like fourth. Not really, but Boyce-Codd normal form is third normal form plus more. And turns out it's actually even easier to describe and just talk about Boyce-Codd normal form, so we will. And that's just named after its inventors. Okay. So what is BCNF? I'll give the kind of more formal definition, and then I'll give the more English definition as I did before. So some relation R with functional dependencies F is in BCNF if for every functional dependency in the closure. So remember, F means I know about, say, a couple of functional dependencies. Use Armstrong's axioms to compute the closure. All the other ones you can infer using those rules. So for every one of those functional dependencies, if it's a trivial functional dependency, or if the thing on the left of the dependency is a superkey, then your table is in Boyce-Codd normal form. So it's a long-winded way of saying it. One kind of simpler way to say this is the only constraints you put on your table are superkey constraints. So let's look at that more in English. Every field of every row, you cannot guess its value using only functional dependencies. You cannot infer its value. So let's look at this. We know that we know some of the functional dependencies. We know that there is one from GPA2 funds. Can we guess the value of these question marks here? Can we guess the funding that Malfoy is receiving? Yes, we can infer that value given other information in the table plus the functional dependency. Since we can infer that value, that means that this is not in Boyce-Codd normal form. That's basically the problem we were trying to solve. Is we don't need to store all these duplicate fund mappings. If I know someone's GPA, I can infer their funds, so I don't need to save the funds along with that row. Okay. After I have decomposed the table, could I remove any cell from either of these tables and then be able to guess its value? Let's pick one. Let's say I remove that cell. Could I infer its value? No. Even knowing all of the functional dependencies that I have and all the other information, it doesn't tell me Ron's birthday. Let's pick another one. If I remove that cell, can I infer its value? No. Same thing goes for a cell on the left side here. If I didn't know that, then if it's not in the table, then I don't know its value. One thing you might be kind of thinking is, well, what if I remove that? That's kind of a gray area. So the way that I have drawn this table, where I know that the primary key is UID, so this table is essentially the primary index. In primary index is ordered based on primary key. We have 1, 2, and then a skip, and then 4 and 5. You could technically infer that the only thing that could be there is a 3, but that's not really what we're talking about. That we can't really infer that. And what if these were not sequential? What if it went 1, 2, and then 17, 18? We don't know what's in between the 2 and the 17.
Does it have to hold true for every row? So like if I could somehow, like if I removed every UID,
If you removed every UID,
would I have to be able to infer every UID? I guess that's my question.
you do this one field at a time. Yeah. So, like if you removed, I mean, but the same logic extends to that. If you removed every UID, could you infer all of the UIDs? No, and you couldn't infer any of the UIDs. But even just doing it one cell at a time, that's kind of what we look at in determining Boyce-Codd normal form. So this is the more like pictorial example way of describing this. This is more useful when you're doing kind of more abstract analysis, and you don't have the luxury of like drawing tables with actual data in them.
So if we now have a dependency on name and GPA, this would not be in this form.
If you had a functional dependency from name to GPA, so if I said name determines GPA, let's see, we do have a violation of that. So if that was a functional dependency, then we could take anyone's GPA and cross it out, and we could infer its value if we somehow knew somebody else named Harry had to have the same GPA 3.9. Yes, that would be violating Boyce-Codd normal form. So to fix that, we would have to decompose again.
Because in the book author, there's only one person with that name.
Yeah, in the book there is only one person with that name, but I don't actually have last names here. I'm sure there's someone else in that universe with the name Harry. No? Bad example then. Okay, so since we cannot guess if any of these values were removed, we could not guess its value. The data would be lost. That means that this is in Boyce-Codd normal form. That combined with the fact that it is also first normal form, second, and third. So first normal form would mean like I cannot put any kind of tuple here. Like maybe I wanted to combine the GPA with the funds into one row. That violates first normal form. So that would also violate BCNF. Okay, so the point of this, one of the points of this was eliminating duplicate information. You're still gonna potentially have duplicate information. Like I have two 1980s stored in here. But there's no way that decomposition would make this any better. If I tried to make some table that maps UID to date of birth or something, then I'm duplicating UIDs unnecessarily. So yes, this is duplicate information, but this is not something that can be solved with decomposition. And that's just the nature of two people can have the same birth date, or two people can have the same name. Okay. So Boyce-Codd normal form lets us say, if my tables are all in BCNF, this kind of gives us a reassurance that redundancy is either basically eliminated as much as it can possibly be, or very limited. And these update, insert, and delete anomalies are gone. So if I change, in this example now, if I need to change somebody's name, there is exactly one place where I change their name. If I change somebody's GPA, there is one place where I change it. And then changing their GPA kind of automatically changes their funding without having to go and change another field. Okay, so your LMS tables are probably pretty close to BCNF, if not actually BCNF, just based on, I've kind of given you all of these rules throughout the semester without formally naming them and being able to analyze them like this. There may be some small violations of BCNF in some of your tables, and if you want to go look for those, like a little functional dependency hunt, that'd be a good exercise. But you do not have to refine your tables at this point to make them BCNF if they're not. Okay. Yep.
How does this, I mean, I'm assuming this works for many-to-many relationship tables.
For many-to-many, that relationship set would be turned into its own table. You would have 3 tables for a many-to-many relationship. You have the entities on the left and right plus a table for the relationship itself. And yeah, this, as long as you know all of your functional dependencies and decomposed correctly, then this works. Yeah, so before, basically the rules were coming from things like what are the keys, are the relationships one-to-many or many-to-many, what are the participation constraints. Now we have these additional possible things like this G to F functional dependency. You can't really express that in terms of participation requirements or keys or anything like that. So this is kind of like a new addition to the language of describing databases that helps us design things in the right way. Okay. So as I said, shorter lecture today, but that's because this pretty much wraps up relational databases. So we're going to talk about non-relational databases next week. Everything we've done has been strictly talking about relations, relational algebra, relational conceptual thinking. You can throw all of that out the door, and there are like actual databases in use that are non-relational. And they're becoming actually more and more popular every day. SQL used to or relational databases used to just dominate everything. Now non-relational databases are kind of looking a lot more interesting. But we'll talk about that